Hey everyone, it's Mr. Glover here. So today we are we're going to talk about solving problems using exponents and logs again, but the emphasis this time is going to be on problem solving, not so much on rearranging the equations. That'll just be part of solving the problems. All right. So usually exponential problems are based on the formula a naught or a equals a naught times 1 plus or minus some kind of percentage to the power t. The percentage change is going to dictate whether you're talking about exponential growth or whether you're talking about exponential decay. If this is a positive, if you're adding like 5%, then you're exponential growth. If you are subtracting, if this was a negative percent, something like a half-life, for example, then you're going to see decay. And we can kind of model this or use this to model different situations. So for example, population doubling every 5 years. In this case, your change in percentage is going to be 100% because you're increasing by 100 or 1. So population doubles, you could write that formula P equals P naught times 2 to the power t. And you could also divide by 5, and then time is going to be a number of years, in this case. If you didn't divide by 5, t would just be like however many periods of doubling. In this case, half-life of fermium is 100 days, so this is a half-life problem. In this question, your percentage is going to be negative 0.5 or 50%. So half-life m equals m naught times 0.5 to the power t over 100. And I'm dividing by 100 because we have a 100-day half-life. Compound interest of 5% on a $2,500 purchase. This one, we can use our compound interest formula, a equals a naught times 1 plus 0.05. That's your 5%. We could assume it's compounding annually to the power 1 times time. And then lastly, compound interest of 5% on $2,500. Similar question. It's just that in this case, this would have been 2,500. In this case, it's compounded monthly. That's the only difference. So it's still a equals 2,500 times 1 plus 0.05. But instead of dividing by 1, we're going to divide by 12 because we're going to compound 12 times a year, and then the power is 12 times t. If both sides are expressed with the same base, we can solve as before. If this is not possible, then logarithms of both sides are required. So, example, an arrowhead found at a Clovis site is tested to find that it contains only 21% of its original carbon-14. If the half-life of carbon-14 is 5,730 years, approximately how old is the arrowhead? All right, so we know 21% is how much is remaining. So m is 21%, so 0.21 times your initial amount, whatever it is. We're going to call it m naught. We know the half-life is 5,730 years. One half-life is 5,730 years. And we need to know how old is the arrowhead. So this is a half-life problem, so we're going to base this on the half-life formula. I'm just going to zoom in a little bit here. We're going to base this on the formula m equals m naught times 0.5 to the power t. And now we can solve for t as number of half-lives, then multiply by 5730, or we can just put it into the formula right off the bat. I think it'll be easier to solve for time and then multiply time by years per half-life. So let's do it this way. We know m is 0.21 of your initial amount, so 0.21 m naught equals m naught times 0.5 to the power t. And we can do a little bit more rearranging here before we take any logarithms. I'm going to divide both sides by m naught. So we get 0.21 equals 0.5 to the power t. Now we can do guess and check, or we can take logs of both sides. That's what we're going to do. So log of the left-hand side, log of 0.21. equals the log of the right-hand side, 0.5 to the power t. And now I can remove t from my exponent. So I can write log of 0.21 equals t times log of 0.5. Lastly, I want to solve for time. So I need to take log of 0.5 and divide it, or divide both sides by it. So log of 0.21 divided by log of 0.5 equals t. And you will find that t is 2.25. Now, we have to remember, we've solved for number of half-lives, so this is just number of half-lives, not number of years. We need to go and take this number, and we need to convert it into years. So we've got another calculation to do. If one half-life equals 5,730 years, 2.25 half-lives equals 2.25 times 5,730, which is 12,901 years. So t equals 12,901 years old. So we need to use the logarithm laws in order to solve this question, but in order to actually solve it, we have to set it up. So this is a perfect example of the kind of problem-solving question that you might see in this chapter. We've got to set up the problem by making the formula for our decay or growth, and then we have to solve for one specific variable in that equation, and we need the log laws to do it. Let's look at another one. Kepler's third law of planetary motion can be expressed as t, or log t, equals 3/2 of log d minus 3.263, where t is the time in years for a planet to revolve around the sun, and d is the average distance in millions of kilometers from the sun. If Mars takes 1.88 years to orbit, what is its average distance from the sun? All right, so we've got a bit of information to unpack here. We've got this equation, and this equation is going to be what we use to solve for distance. We know that Mars has a 1.88 year orbit, and t is the time that a planet takes to revolve around the sun. So in this case, I know t for Mars is 1.88. And now this equation looks pretty ugly, but literally there's only two variables. There's t for period and d for distance. We know the period of time, so we have to solve for the distance. So we just need to take the formula. We'll write it out in its full glory. So log of t equals 3/2 log d minus 3.263. And then I'm going to plug in my 1.88 for time because I know that that's the period. So log of 1.88 equals 3/2 log d minus 3.263. So now we have to do a bunch of rearranging, and we have to solve for distance. So I'm going to add 3.263 to both sides. Log 1.88 plus 3.263 equals 3/2 log d. Okay, and now I'm going to multiply by 2/3 to eliminate 3/2 on this side. So 2/3 times log 1.88 plus 3.263 equals log d. Okay, so now at this point, you've got a choice. Technically, we should leave this in one expression. Don't calculate anything till the last step. This is going to become an exponent because we have to convert to exponential form to solve for d. If we're comfortable putting in our calculators, we can simply just plug this into our exponent. However, most people might have trouble with this. So I'm just going to turn it into a decimal. I'm going to turn this into 2.358 equals log d. Technically, we don't need to do this, and technically we're actually going to make it less exact by doing it, but it'll make your life a lot easier. Now we can go to exponential form. we can simply go 10 to the 2.358 equals d, and we get 2.28 million kilometers, or 228, sorry. That's d. And so going back to what the question is asking, if Mars takes 1.8 years, what is the average distance from the sun? Well, the distance is in millions of kilometers, so distance is 228 million kilometers from the sun. It's probably okay for us to do some rounding because we're already rounding to nearest million. But if you were planning on doing something that needs precision, like launching a satellite or something like that, you're going to have to make sure you don't plug any numbers in until the very last step. Oops. Recall when we used exponential equations to solve problems involving compound interest. So you might remember these equations from before. We did them at the start of the chapter, but we couldn't solve for time at that point because at the start of the chapter, the only solution or the only strategy we had to solve for exponents was to graph or to use guess and check. Now we've got the option to actually plug or use logarithms and plug numbers into our calculator to solve it rather than actually kind of using a roundabout kind of strategy. So we're going to go back to these questions and we're going to specifically solve for time because that's the thing we weren't able to solve for before. So let's try one. Ben has always wanted to play goalie on his hockey team, but he doesn't have a set of pads. Tyler decides on a set of pads that cost $6,000. He only saved $5,000. We'll pretend that says Ben. Ben decides to deposit his money in a bank account with an interest rate of 6% compounded monthly. How many years will he have to wait until he can realize his dream? All right, so let's list out the variables first. We're going to be basing this on the formula A equals A naught times 1 plus I over n to the nt. And we can list out what we know. So A is the future value. That's what we want to have. A is $6,000. A naught is 5,000. That's how much Ben started with. Interest rate I is 6% compounding monthly. So I is 0.06. N is number of compounding periods per year, and N is 12 because we're compounding monthly. T is our unknown. T is what we're trying to solve for, okay? So let's put all these variables into our equation and solve for time. I'm just gonna zoom in a little bit. All right, so A is $6,000. That equals A naught, which is $5,000, times 1 plus 0.06 over N, which is 12, to the power 12 times T. And now we've got to do some rearranging. I'm going to get rid of 5,000 by dividing it away. So divide both sides by 5,000. 6,000 over 5,000 equals 1 plus 0.005 to the power 12t. We can do a bit more simplifying. 6,000 over 5,000 is just 6 over 5. That equals 1.005 to the power 12t. And now we're at the point where we can take the log of both sides. We need to get access into our exponent. So take the log of both sides. Log of 6 over 5 equals log of 1.005 to the 12t. We can now remove our exponent using the power rule. So log of 6 over 5 equals 12t times log of 1.005. And now we need to get rid of the 12 and the log in order to isolate time. I'm just going to divide them at once. You can do it in 2 steps if you want. So log of 6 over 5 divided by 12 times log of 1.005 equals time. All right, so now we have to put this in our calculator. We can do it in one shot and we'll get a little bit of a more precise answer. 3.04 equals time. So what we've actually gone and found is that Ben can buy his pads in t equals 3.04 years. Before, we would have gotten to this point right here, and we would have had to use guess and check, or we would have had to graph the function to solve for time. Excuse me. We can also use logs and exponents to model more realistic financial situations. So up until this point, we have been restricted to this compound interest formula. As it turns out, that one's not necessarily the most useful because it's only based on a one-time deposit. It's based on putting money in the bank once with a steady interest rate and just sitting on that money. Most people don't have $6,000, $10,000, $20,000 to just throw into the bank. So most people are going to have to save by making payments or regular deposits. That opens the door to more complicated expressions. And up until this point, we haven't really had the ability to solve for any variables in those expressions. Now we do. So this is going to lead us to the future value and the present value formula. The future value is based on making regular payments towards something. So you're saving. Interest is going to be your friend in this case, and it's a matter of making regular payments with interest to get up to a certain goal. The present value formula, which is the one that we'll do next, or afterwards, is similar to the future value formula. This is when you're paying off a debt. And the difference here is that interest is going against you. Rather than having interest help make your money slowly grow, interest is slowly clawing some of that money away so that you actually are paying back less over time. So let's take a look at future value. So when a series of equal investments is made at equal time intervals and compounding period for the interest is equal to the time interval for the investments, we have the future value formula. It's given by the formula FV, future value equals R, your regular payment, times 1 plus I to the power n minus 1 over I. And now there's a few things that you really have to be careful with. This formula is only valid if you are using the same time intervals for your investments as you do for the interest compounding. So technically, this will change slightly if your compounding periods are different than your interest, than your payments. Weird. I'm not going to give you questions like that, but if you go to use this in real life, just realize that it's going to be off by a small amount. R is your regular payment, and it needs to be the same investment every time. Interest rate I is really important. So I is your interest rate per compounding period. Super important. Per compounding period means you need to divide I by n before putting it in this formula. N is the number of investments. It's also the number of compounding periods. All right, let's put this to the test. So Anakin really wants to buy a helicopter so that he can go sledding high up in the mountains. He found one in Grand Prairie for $100,000. Anakin decides to start saving, so he opens a savings account. If Anakin deposits $100 each month into the account and he gains 6% annually compounded monthly, how long will he have to keep making deposits before he has enough for his helicopter? So let's list out what we know. He's going to have a future value of $100,000. So FV equals $100,000. He's making a regular payment of $100. So R is your payment. R equals $100. He's making 6% annually compounded monthly. So I is 0.06 divided by 12, which I believe is 0.005, which is 0.005. How long will he have? And we need to solve for n, which is our unknown. N is the number of compounding periods or number of payments. So let's start with the compound or future value formula, plug in what we know, and solve for n. So let's kind of portion this off to the side. All right, so we know future value, FV, equals r times 1 plus I to the power n minus 1 all divided by I. Now let's plug in what we know. Future value is 100,000. 100,000 equals R, which is 100, times 1 plus I, 1 plus 0.005, so power n minus 1, all divided by 0.005. Okay, so now we need to systematically remove parts of this equation until we can get down to the brackets with n. So I'm going to multiply by 0.005. 0.005 times 100,000 equals 100 times 1 plus 0, or I'm just going to write this as 1.005 to the power n minus 1. And let's use square brackets to keep it consistent. All right, now I need to divide by 100. So 0.005 times 100,000 all divided by 100 equals 1.005 to the power n minus 1. Okay. 0.005 times 100,000 divided by 100 is just 5. So 5 equals 1.005 to the n minus 1. I can add 1 to both sides. So 6 equals 1.005 to the power n. And now we need to take the log of both sides. I'm kind of running out of space here, so I'm gonna move over. But I'm gonna go log of 6 equals the log of 1.005 to the power n. I can now remove n. I can use the power rule to pull it out front. So log of 6 equals n log 1.005. I can divide by the log of 1.005. Log of 6 divided by log 1.005 equals n. And lo and behold, 359.25 payments. Okay, so we have to kind of put the context back into this question. You don't have a quarter payment, so you're going to have 360 payments. We need to divide by 12, so 360 payments divided by 12 payments per year. That gets me about 30 years. And so our final answer is that n is approximately 30 years. So if Anakin puts $100 a month into a savings account, in approximately 30 years, he will have his $100,000 for a helicopter. Now that's not very much money every month, and it's a 6% interest, so it's doable. Keep in mind that in 30 years, $100,000 will be less valuable than it is, and also keep in mind helicopters probably cost more than $100,000. But for this make-believe question, 30 years is fairly reasonable. Okay, in addition to the future value, we can model the repayment of a loan by using the present value formula. So present value, when a loan is taken out of the bank or taken out from the bank, the amount borrowed is known as the principal value. If a series of equal payments is made at equal time intervals and compounding period for interest is equal to the time interval for the payments, so the same thing, time intervals for payments equals time intervals for compounding periods, then we can use the present value formula. The present value of the loan tells you how much the loan is going to be worth at a given point in time. R is the dollars, regular payment, I is the interest rate per compounding period, and N is the number of payments. All right, so let's give this one a try. Nellie really wants to buy a house in Fort St. John. Since the market is down, she managed to find a house for $200,000. She can afford a monthly payment of $1,500, and the mortgage will be paid with equal monthly payments at 4% interest, compounded monthly. How many monthly payments will Nellie need to make? When will she have her house paid off? Okay, so in this case, the present value of her loan is $200,000. You can use this in two different ways. If you start with the present value of your loan value, you can solve for N to figure out the term. If you know N, let's say that you know you've paid for 60 months, you can plug N in and solve for what is the value of the loan now. So that those are the two reasons why you'd probably use this formula. You probably want to figure out after 6 years, how much of my house do I have to pay off? That's solving for present value. Or you probably want to know if a house is 200 grand, how much time is it going to take to pay off? That's solving for N. So we know the future or the present value is 200,000 because that's what her loan's worth. So PV is 200,000. She's making $1,500 payments. So R equals $1,500. She's paying monthly, 4% interest compounded monthly. So your interest rate I is 0.04 divided by 12, which probably isn't going to be a nice number. Oh, of course not, 0.0033. And we don't know N. N is what we're trying to find. All right, so let's write out our formula, present value formula. So present value equals R times 1 minus 1 plus I to the power negative N, all divided by interest rate I. And now let's plug in our numbers. Present value is 200,000. Separate this here. So 200,000 equals R, so 1,500, times 1 minus 1 plus 0.0033, repeating, to the negative N, all divided by 0.0033, repeating. All right, so now just like before, I'm going to multiply by the denominator and divide by 1,500. I'm going to do it in one shot though, just because I don't have a lot of space to work with here. So 0.003 repeating times 200,000, all divided by 1,500, equals 1 minus 1.0033 repeating to the negative N. The left-hand side is going to become 4 over 9. And you can multiply this in, and then you can try to write it in lowest terms. You could also leave it as a decimal, but this will be a little bit more precise if we leave it as a fraction. So 1 minus 1.003 repeating to the negative N. I'm going to now subtract 1 from that. So 4/9 minus 9/9 is negative 5 over 9 equals negative 1.003 repeating to the negative N. I need a little bit more room, so I'm going to move up to the top again. So I can get rid of my negatives. I can just multiply both sides by minus 1. 5 over 9 equals 1.003 repeating to the power negative N. Take the log of both sides. Log of 5 over 9 equals log of 1.003 repeating to the negative N. I can now remove my exponent. Log of 5 over 9 equals negative N log 1.003 repeating. And now, lastly, I can divide by log of 1.003 and the -1 to isolate n. So log of 5/9 divided by negative log of 1.003 repeating equals n. We can plug this into a calculator and we will get 176.6. So it's approximately 177 payments. Now we've just got to go back to what the question's asking. How many monthly payments will she need to make? When will she have her house paid off? Okay, so 177 payments is the answer to the first part. Oops. If we divide 177 by 12, it's going to take 14.75 years to pay off. Which is actually pretty good. If she can pay her mortgage off in less than 15 years, she's probably going to be in pretty good shape once that mortgage is done. It's kind of a sobering thought to think about. If you have a 25-year mortgage on your house, you're paying that for 25 straight years. 177 payments seems like a lot, but you're not quite doubled, but almost double that much if you pay for 25 years. Okay, so I think that's where we'll stop things. This will give you a bit of a taste of the kinds of problems that we're going to solve in this chapter. So some of them are going to be where you have to actually model the equation yourself. So that was the first kind of question where we had to build the equation, whether it was a half-life problem, or whether it was one that was given to us, or maybe it would have been a doubling problem, and then solve for time. And we also spent some time with the compound interest formula, and then we talked about future value and present value. By the way, if this, in a normal situation, if I had given you questions like this on the test, I don't expect you to memorize these formulas. You would be given present value and future value. You would just have to know how to use those formulas. Okay, so try page 477, 3 to 9. 10 and the multiple choice are going to be extras. They're not required questions, but they're suggested problems. So have yourselves a great rest of the day. I will see you all in our chat tomorrow. And yeah, just shoot me an email if you've got any questions. Bye for now.